Welcome everyone. In this video, we will demonstrate how to measure the attenuation of an unknown attenuator. We will use a 6 dB fixed attenuator and the calibrated variable attenuator for this purpose. The variable attenuator was calibrated in experiment 4. The method is going to be used in this experiment is called the RF substitution method. You supposed to introduce with SWR meter in this experiment, but we will not use that meter right now because the crystal detector, which is an essential equipment for the SWR meter, is not working properly. We will modify the experimental setup slightly because of the broken device. Instead of the crystal detector and the SWR meter, we will use the thermistor mount and the power meter. In this method, the component whose attenuation is to be measured, such for example the unknown attenuator, is inserted between a source and the calibrated variable attenuator and a detector. Then the variable attenuator is adjusted to produce a convenient signal level at the detector's output. Finally, the unknown attenuator is removed from the setup. As we remove the unknown attenuator, the signal level will go up, and then we will use the variable attenuator to reduce the signal level and bring it down to the same level that we obtained before while we were using the unknown component. Now, for both cases, we have the same signal level, meaning that we got an substituted, we got an equivalent circuit for two different cases. The first case was with unknown attenuator and the second case was with the calibrated variable attenuator. And both cases we got the same power level. That means we have substituted the RF component. That's why it is called RF substitution method. And as these both circuits are working, providing same power level, that means they have same attenuation. So now we read out the attenuation obtained for variable attenuator and see the variable attenuator's blade position and find the power or insertion loss at that position from the calibrated graph. For example, if you get the blade position at 2 millimeter and from the graph you find that at 2 millimeter the insertion loss or attenuation is 5 dB. That means that the unknown component attenuation is 5 dB. So here this is the experimental setup for attenuation measurement. So in this setup you will see the microwave source is the GAN oscillator, is the microwave signal source, and after that we will use an unknown attenuator, and right after that we have a calibrated variable attenuator and then the signal detector and the meter. So instead of detector and meter, we will be using here thermistor mount and power meter. So that's why our signal level should be relatively higher because a crystal detector and SWR meter can measure the very low signal, but power meter or thermistor mount cannot detect that low level signals. So that's why we need to modify our circuit a little bit. Here you can see the experimental procedure. In the past, we have to turn off all the meters and devices, and we require gun oscillator power supply and HWR meter. But instead of HWR meter, we will be using power meter. So we have to make some settings like this. So the gun oscillator power supply, we choose 10 volt range and mode should be 1 kilohertz. And for SWR meter, the some settings are told here, but uh, we don't need SWR meter right now. So we'll be using power meter. Here you can see the experimental setup for attenuation measurement. As we are using crystal detector and SWR meter, we could have a lot of attenuator in this circuit. For example, here you can see a 30 dB attenuator, a 6 dB attenuator, and variable attenuator. So the total attenuation, if you sum up, that will be higher than 36 dB. But our power meter cannot measure that levels of signal. Only the SWR meter can detect a signal level up to negative 70 dB. But the power meter that we have in the lab can measure only negative 30 dB, sorry, negative 20 dB. So that's why we removed this 30 dB from the setup and replaced this crystal detector with thermistor and SWR meter with power meter. So the experimental setup that we prepare for this experiment should include gun oscillator power supply, a 6 dB fixed attenuator, and a variable attenuator, thermistor mount, and HWR meter. So we remove this 30 dB fixed attenuator and replace the crystal detector and HWR meter with thermistor and power meter. This step 4 and 5 is particularly for the HWR meter. So we don't use this. You can skip these steps for this time being. We can skip step 6 too. But for step 7, it is said you have to set the variable attenuator at 0 millimeter position. So we set the variable attenuator at 0 millimeter position. You can skip step 8 and step 9. You can skip this setup too, because this setup is for measuring the insertion loss of the 6 dB fixed attenuator. So we will skip this step also. Here you can see the experimental setup. So we have a variable attenuator, thermistor mount, and a 6 dB attenuator, and we connect it to the power meter. So right now we are adjusting the power meter to 0 using 0 adjust knob, and we are using 10 milliwatt range. So the power variable attenuator is set at 0 millimeter position now, and this is the 6 dB attenuation. We are going to measure the attenuation of this device. So at this stage we get the power level of negative 5, so that will be positive 5 dB. So this setup produce 5 dB power. Now we are going to remove the fixed attenuator. So we are taking off the 6 dB attenuator from the setup. So as the attenuation is less than the previous case, so the 6 dB is taken off. So as the 6 dB is off, now we have only variable attenuator. And so if you look at the power level now, the power level is higher than the previous case. So it is like almost 8 dB. So because we have removed 6 dB, so it is obvious that power level will be up. So now I am using variable attenuator to bring the power level back to the previous value. So I'm playing with the variable attenuator. Now you see the power level hit up the previous point. So now read the value from the variable attenuator, the blade position from of the variable attenuator, and record this value. This value is 1.95 millimeter. So in step 10, we have to record the variable attenuator blade position that is required to get the same power level when we had used the variable attenuator blade position. At this position, we got the same power level of the unknown attenuator. So we record that position here, and then from the calibration curve that we have obtained in exercise 4, look from that calibration curve, see at that millimeter position what will be the insertion loss. Insertion loss is 6.9 dB. That is obtained from the calibration graph. We record the insertion loss value here. At the table 4.1, you will find the attenuation of that variable attenuator for 0 millimeter position. So that's called the insertion loss at 0 millimeter. For this particular attenuator, we had 0.8 dB attenuation for 0 millimeter position. Now we subtract the value because for these two values, and we get the difference here, and this difference will be equal to the value of the unknown attenuator, and which is 6.1 dB. We got the value for unknown attenuation is 6.1 dB, which is very closer to the actual number.